Hi, everybody. This is example 11.1, and I'm going to pause because I can't find my pen. All right, example 11.1. They call it walking the plank. And they say, a uniform plank of length 6 meters, 6.0 meters, and mass 90 kg. Rest on shoulders is separated by E equals 1.5 meters. Cousin Throckmorton wants to stand on the right hand end of the plank. If the plank is 3 minute rest, how massive can Throckmorton be? So here's what we got going here. You got this plank. Your mass is 90 kg. The length is 6 meters. Let me put that M there. And you got a couple pivots on it, equidistant from the center. And this guy in between is what? 1.5 meters. So that distance to there is 1.5 meters. All right. How massive can, this guy, your cousin, Throckmorton, and I've never heard that name before, but okay, he's standing here. And how massive can he be without making getting slapped in the face by the other end of the plank? All right. So in order to balance this, we got to have the center of mass over that point, center of gravity over that point. So we're going to take this guy, the origin, and we call it C. And then we take Throckmorton, and let's call that XP. If I'm not mistaken, and let me make sure I'm not mistaken. All right, so we have the Throcky, we're going to call this X equals 0. And this guy is going to be X equals 3. And so here we're going to be equals D over 2. So that's going to be, let's see, do we have a value for that? We're just going to call this D over 2. Okay, now we're going to use equation 11.3 to locate the center of gravity. And we have, this is the equation, by the way. All right, so the summation of the individual masses times X is going over the summation of the masses is going to be equal to the center of gravity. So what we have going here is XCG equals M at the origin plus M at L over 2, that's the Rocky, right? Over M plus M. And this is the average, this is the center of mass of the plank right there, right? That's the whole 90 kilogram plank, but right in the center, so we're calling that 0. And that's going to equal, I'm going to go down here, M, that's going to equal M over M plus M times L over 2. Now, the thing is, we've already established it's got to be over the right solvers, which is a distance of D over 2 from the center. I'm going to go ahead and set that equal to that. I know where the center of mass has to be, and I'm just going to solve for the boy's mass, the boy's mass, all right? So his little m is going to be equal to m times d over L minus d. And that's going to be equal to 90 kg, the mass of the whole thing, times 1.5 meters divided by 6 meters minus 1.5 meters. And my answer is going to be 30 kilograms. Oops. So, you know, that's a lot. So he can be a pretty big little boy. All right. Thank you kindly. We'll go on to the next. 11.2 is called locating your center of gravity. And it reads, the plank in figure 11.8 is a great way to strengthen abdominal, back, and shoulder muscles. You can use this exercise position to locate your center of gravity. All right, this is question 11.2. Locating your center of gravity while you work out. And what do we have going here? It says, the plank is a great way to strengthen abdominal, back, and shoulder muscles. You can also use this exercise position to locate your center of gravity. How holding plank position with the scale under his toes and another under his forearms, one athlete measured that 66% of his weight was supported by his forearms and 34% by his toes. That is, the total normal forces on his forearms and toes were 0.66 weight and 0.34 weight respectively, where weight, W is the athlete's weight. He is 1.8 meters tall, and in plank position, the distance from his toes to his forearms is 1.53 meters. How far from his toes is the center of gravity? Let's see what we've got going here. We're going to do a free body diagram. All right. That's the athlete. These are the toes. You got a normal force here, which is, he's in static equilibrium. That's going to be equal to 0.340 weight. You got the center, okay, you got the forearms here. You got a normal force there. And that's going to be equal to 0.660 weight. Then the center of gravity is going to be somewhere closer to the force that's supporting the lion's share of the weight. So you got your CG here. And that's going to be where the weight is centered, if you will. Now we're going to do this sum of the forces in the X, the sum of the forces in the Y, and the sum of the torques. So we've got sum of the forces in the X is going to equal to 0. There's no forces in the X. They're only in the Y. Sum of the forces in the Y are going to equal to 0.340 weight plus 0.660 weight minus W equals 0. That just totally makes sense. Now let's do the sum of the torques. And we're going to take the torque about this point. All right, so we're going to have that's going to be equal to 0.340 weight times 0, because this is going to be our point about which we're taking it, and minus weight, and I guess we're calling this location of CG, this, weight times LCG, plus 0.660 weight. And we were given in the problem that this distance is 1.53 meters times 1.53 meters equals 0. So now we're going to get weight times LCG equals 0.660 W times 1.53 meters. And then you divide both sides by weight, and you're going to solve for LCG is going to be equal to 1.01 meters, 1.01 meters. That was 11.2. Okay, this is example 11.3, and it's will the ladder slip? Sir Lancelot, who weighs 800 newtons, I'm going to save this for all these values for the free body diagram, and I'm going to put them all on the free body diagram. Is assaulting a castle by climbing a uniform ladder that is 5 meters long and weighs 180 newtons. The bottom of the ladder rests on a ledge and leans across the moat in equilibrium against a frictionless vertical castle wall. The ladder makes an angle of 53.1 with a horizontal. Lancelot pauses 1/3 of the way up the ladder. Find the normal and friction forces on the base of the ladder. Find the minimum coefficient of static friction needed to prevent slipping at the base. Find the magnitude and direction of the contact force on the base of the ladder. All right, so our free body diagram is going to look like this. Let me get back. We're going to have your ladder. This guy is 53.1, I believe. 53.1 degrees. And here's the floor. Here's the castle. That doesn't look like a 53.1 degree angle, but just use your imagination, if you will. I'm going to change colors and draw my forces. Okay, I've got we're calling this guy N2. N2. And we're calling this, there's static friction here, FS. We've got, he's up 1/3, so we've got, he's 800 newtons. And this is a 3, 4, 5 triangle. So if he's up 1/3, this is going to be the 3 side. So this distance, and I'll do that in a different color. This lever arm right here is going to be 1 meter, right? Because this is 1 meter. And then let me go back to my other color. The weight of the ladder is centered right in the middle, right there. And this is 180 newtons. And so its lever arm is going to be a half of that 3 meter leg. So we'll go ahead and put that in red. And that's going to be 1.5 meters. All right. We've also got a normal force from here, from the castle wall going this way, producing a torque going in a counterclockwise direction. And its lever arm is going to be this 4 meters, a 4 meter leg, right? And we'll go ahead and do that. There we go. So I hope this is pretty easy to understand. All right, continuing on. We're going to draw our conditions of equilibrium. So the sum of the forces in the X, the sum of the forces in the Y, and the sum of the torques. Some of the forces in the X are going to equal to that force of static friction, that's going in the positive direction. And then minus that normal, oh, this is N1, that's N2. Minus N1, that's going to equal to 0. The sum of the forces, this is X, in the Y are going to be equal to, you got your N2, it's going in the positive direction, minus 800 newtons, minus 180 newtons, and that's also going to be equal to 0. Now you're going to take the sum of the torques. Sum of the torques about this point here, right? This is where it's going to slip. We're going to have N1 times a lever arm of 4 meters. That's going to give you a counterclockwise torque, and that's going to be positive. And then you're going to have these clockwise torques, and they're going to be negative, minus 180 newtons for the weight of the ladder, centered all at the center of gravity or center of mass there, which is smack in the middle, having a lever arm of 1.5 meters. Also minus 800 newtons. And that's going to be times 1.0 meters. Now we can go ahead and use that bottom equation to solve for N1. And the value is going to be 268 newtons. And we go ahead and put this in here. So you're going to get your F of S is going to be a negative, or, oh, I'm sorry, that's going to be 268 as well. 268, right? Because this is going to equal that, newtons. All right. All right, so we have our force of static friction is that, and by definition, N mu S equals F of S. So we're going to have mu S equals F of S over N. And we know that N is, from the other equation we can use and solve here. So we're going to get N2 is equal to this plus that. It's going to be N2. This is N2. N2 is going to be equal to 980 newtons. So mu S is going to be equal to 268 newtons over 980 newtons. And that's going to give us 0.27. So mu S equals 0.27. And that's a unitless number. Oh, I can see that I stopped my recording and I don't know where I stopped it. So I'm just going to go ahead and solve and talk you through this whole thing. All right. I was to solve for the friction force here, about this point, right? Or right here. This is frictionless. So what we did was we took the sum of the forces in the X, the sum of the forces in the Y, and the sum of the torques. So in the X, I have this guy here, the friction, and this guy, and here we have the friction's going in the positive direction. The frictional force minus this normal force up at the top of the ladder, that's going to equal 0. And the sum of the forces in the Y, I've got this normal force here we called N2. That's in the positive direction, minus 800, that's the weight of Sir Lancelot, minus 180, and that's the weight of the ladder, and that equals 0 because the system is in static equilibrium. Now the sum of the torques, I used N1 and times 4 meters right here. Okay, we're going to take the torque about this point. So N1 is going this way, producing a positive torque, counterclockwise. So this is, and the lever arm is 4 meters because this is a 3, 4, 5 triangle. So that's this guy. Now 800 is going to go produce a clockwise torque, and its lever arm is, remember, he was 1/3 of the way up the ladder. So it's going to be 1/3 of this distance, which is 1 meter. So it's minus 800 times 1 meter. Then we've got 180 newtons, and that's halfway up the ladder. So its lever arm is going to be 1.5 meters. All right, so we have the sum of the torques is that positive guy and minus these guys. Now, I took this equation, solved for N1, and I don't see, N1 equals 268 newtons. I went back and solved for Fs here. So I had Fs equals 268 newtons. All right, now I need to solve for my coefficient of static friction. So by definition, this would be N2, the normal force, times mu S. So I needed to take my value for N1 and go, oh no, just solve for the normal force here. So I solved for N2, and got 980 newtons with this equation. So now my normal force times my coefficient of static friction is going to equal my force of static friction. So to solve for the static friction, I took the coefficient of static friction. I took the force of static friction divided by the normal force, and I got 0.27 for mu s. Finally, I had to solve for the force here. So I took all the forces around about that point. So it would be the force of static friction I in the I direction plus the normal force in the J direction. And we had a 268 newtons I plus 980 J. And then I took, and they're both positive, and to get the magnitude, I converted those Cartesian coordinates to polar and got this value, 1020 newtons. That's the magnitude. Then to get the direction, I took the tan inverse, like we always do, of the y coordinate over the x, and my angle was 75 degrees. Okay, so that was a very colorful 11.3. This is example 11.4, and it is called equilibrium and pumping iron. Okay, and so what we have here is a weightlifter. So there's a horizontal human arm lifting a dumbbell. The forearm is in equilibrium under the action of the weight of the dumbbell and the tension T in the tendon connected to the bicep. And a little disclaimer here, they have that tension like in the middle of the forearm, and they say tendon actually insert close to elbow, moved here for clarity, because you can't have your tendon connected to your shoulder from the middle of the forearm. That just wouldn't work. Anyway, let's see. So that's my disclaimer, and or their disclaimer. We are to solve. I'm going to draw the free body diagram. There's a. Let's see. Let me just go ahead and read it. The tension in the tendon connected to the bicep, the force exerted on the forearm by the upper arm at the elbow joint. We ignore the weight of the forearm itself. For clarity in the drawing, we've exaggerated the distance from the elbow to point A where the tendon is attached. Given the weight W and the angle theta between the tension and the horizontal, find T and the two components of E. So 3 unknown scalars. So the free body diagram looks like this. It's an arm that is bent at the elbow. And okay, so that's the arm. So I'm going to do different colors so I hopefully make it clearer. So I'm going to draw the forces here. You've got, this is a hand and it's holding weight. So that's a force of weight there. And once again, that tendon force is probably should be right there, but they've exaggerated here. And this is going this way. T. Then we have a force of on the elbow exerted by the force E exerted by the forearm on the upper arm, and that acts here. We're calling that E. It acts at the elbow. All right, we've got an angle. Let me change colors. You've got an angle here, theta. And we've got, let's see. We're going to break it up into its components, so I'll go ahead and do that. Yellow. I've got a force E to the X here, EX here, and I've got a force EY here, and I've got a force TY going that way and TX going that way. Okay, so let's see. To find T, we're going to take the torques about the elbow. So the torque about the elbow doesn't contain this force, right? Because this force acts right at the point of rotation. So let's go ahead and do that. The sum of the forces of the torque at the elbow is going to equal to Oh, I've just got to give you some more things. I got to give you some. This is called L right here, this length. And let's see, we've got this length right here is going to be called, let me do that in a different color. This length right here is going to be called D. Okay, so that should clarify things. We've got LW, so the weight times L, LW, minus DT. Remember, because T's going minus D times T. All right, LW is producing a counterclockwise torque, and T is producing a clockwise torque. That's why we have a positive LW minus DT. And that's going to, this is T sub Y, my bad. And that's going to equal to 0. And let's see, they solve this in terms of T sub Y. T sub Y is going to equal to LW over D, LW over D, and that's going to equal to T sine theta. All right. All right, now continuing on to solve for EX and EY, we're going to use the sum of the forces in the X and the sum of the forces in the Y. So the sum of the forces in the X are going to be equal to T sub X. T sub X goes in, T sub X goes in, yeah, the positive direction. Yes. T sub X, sorry, minus E sub X, and that all equals 0. And the sum of the forces in the Y are going to equal to negative W plus T sub Y plus E sub Y, and that's all going to equal to 0. All right, and for T sub Y, let's see, we're going to substitute that LW. Oh, no, we're not. What are we going to do? Hang on, let me pause it and make sure. All right, so I was solving for the sum of the forces. I'm solving for E sub X. So I have a T sub X equals E sub X. And let's see, T sub X, we're going to use this value for T, which is going to be, wait, what? I think I'm messing up here. Hang on, let me pause. Okay, so what I'm doing here is I'm solving for T here. All right, so T is going to be equal, let me put this here, T is equal to LW over D sine theta. All right, so T sub X is going to be equal to T cos theta. So E sub X is going to be equal to LW over D, and then that's going to be cos theta over sine theta. So that's cotangent. So that's going to be LW over D cotangent of theta. All right, and that's E sub X. All right, for E sub Y, let's see. We're going to have a T sub Y, which I've already defined as LW over D. So negative W plus LW over D equals negative E sub Y. So let's see, let's go ahead and do that by a negative and there. And E sub Y equals W minus LW over D. I guess they're just multiplied through by a common denominator. So what they did was WD minus LW over D equals E sub Y. All right, and that was 11.4. 11.5 is called tensile stress and strain. It says a steel rod 2 meters long has a cross-sectional area of 0.3 centimeters squared. So 2.0 meters, and This is L, and A equals, and I really don't like this mixing of units, but 0.30 centimeters squared. It is hung from one end by a support, and a 550 kilogram milling machine is hung from the other end. So W equals, or no, M equals 550 kg milling machine. Determine the stress on the rod and the resulting strain and elongation. Okay, let's go ahead and do that. Okay, so I know that I'm going to have to convert this into meters squared. So let's see, 100 centimeters quantity squared equals 1 meter squared. So that's going to give me 0.3 times 10 to the negative 4th meters squared, and 3.0 times 10 to the negative 5th meters squared. Okay, so it's being pulled. It's under tension, so we're going to use the equation for tensile stress. T equals F perp over A, and that we're hanging something for the force. So this is going to be 550 kg times 9.8 meters per second squared, divided by A, which is 3.0 times 10 to the negative 5th meters squared. And so our tensile stress is going to be 1.8 times 10 to the 8th pascals. All right, and then strain is going to be equal to the stress over the Young's modulus. It's equal to delta L over L original, or the stress over the Young's modulus, which is in the table, and that's 1111. That will be here. Let's see. We got table 1111. Gives you all the Young moduluses for various materials. Steel, we got 220 times 10 to the 10th. Okay. This is going to be 1.8 times 10 to the 8 pascals times 20 times 10 to the 10th pascals equals 9 times 10 to the negative 4th, 9.0 times 10 to the negative 4th. All right, and now I guess we want the elongation. So the elongation is delta L. So we're going to use that strain times the original length, strain times L original equals the elongation. So we've got 9.0 times 10 to the negative 4th times 2.0 meters. That's going to be equal to 1.8 millimeters. That's 11.5. Okay, now we're going to do example 11.6. Hang on, let me make sure I'm recording this. Okay, I am. Last time I had to do it twice. Well, it's called bulk stress and strain. All right, and it says a hydraulic press contains 0.25 meters cubed, 250 liters of oil. So we've got 0.25 meters cubed. Find the decrease in the volume when the oil is subjected to a pressure increase of delta P equals 1.6 times 10 to the 7th pascals. The bulk modulus of oil is B equals 5.0 times 10 to the 9th pascals. Okay, and its compressibility is K equals 1 over B, which is, they solved this, this is pretty great, is going to equal to 20 times 10 to the negative 6 ATM. ATM, the negative 1. So they converted it from pascals to atmospheres and then took the reciprocal. Okay. So we want to know the change in volume. So it's given by delta V equals original volume times the change in pressure divided by the bulk modulus. So that's going to be equal to, here we go, 20, let's see. They, okay, so they just used K instead of B. Okay, so, but we'll go ahead and you can do it either way. K is just reciprocal of B. So we're going to have 0.25 meters cubed times 1.6 times 10 to the 7 pascals divided by 5.0 times 10 to the 9th pascals. And we get equals negative 8 times 10 to the negative 4th meters cubed. Okay. And they did another calculation where they used K, which is in the value over atmospheres. But they got the same value and it worked out fine. All right, thank you.